All right, so last time we started taking a look at section 1.1, which is a preview of calculus. And I didn't have a chance to show you these images, but let me just kind of run through them with you really quickly. I mentioned some of them. These are the ideas of what you can do with calculus versus what you're limited to being able to do without calculus. So if you see what's on the left, those are the pre-calculus ideas that we talked about. So on the left, you can find the value of a point on the curve, but on the right, you can find the limit, what it gets really close to. Sometimes those are the same thing and sometimes they're not. On the left, you can find a slope of a line with pre-calculus. On the right, you can find the slope of a curve, how a curve is changing. On the left, you can find, with pre-calculus, you can find secant lines, and with calculus, you can find tangent lines, as we mentioned. And then there's a bunch of others here, so let me just run through them real quick. You can find average rate of change versus instantaneous rate of change. Instantaneous means at a specific point in time. If any of you have the cars where it tells you exactly how fast you're going, like on your speedometer, like right there beside it, that's instantaneous rate of change. Curvature of a curve, or of a circle versus curvature of a curve. The height at a specific point, much like the very first example, versus the maximum height on a curve. A tangent plane on a sphere compared to a tangent plane on any surface. The direction of motion along a line compared to along a curve. Area of a rectangle versus area under a curve. That's what we'll get to at the very end of Calc 1. The work done by a constant force compared to work done by a variable force. The center of a rectangle compared to the center of a region. And then the length of a line segment compared to the length of an arc. I think I mentioned that one specifically last time. Surface area of a cylinder compared to the surface area of any solid. The mass of a solid of constant density compared to the mass of a solid of variable density, where the density throughout the object changes. The volume of a rectangular solid compared to the volume of a region under a surface, so the volume of any sort of random shape is the idea. This last one on this, some of these are Calc 2 concepts, most of them on this screen are. The last one's actually Calc 3, at least we do it on our Calc 3 class. The sum of a finite number of terms is pre-calc. The sum of an infinite number of terms is calculus. And we started this. So we got to the tangent line problem and I was on the area problem. Yep. Okay, so we're going to jump in right here. Turn the screen. Okay, and like last time, I'm going to talk about what happens in calculus compared to pre-calc on an area problem. So in pre-calc, we can find the area of certain shapes. Very specific shapes, like, this is not an exhaustive list, but just some examples. Like rectangles, right? We know how to find the area of rectangles. Triangles. Circles. I'm going to put etc. because there's clearly others that I could add to this list, but we're not going to list everything. Because there's a bunch of formulas, you can find areas of certain things, and you did that probably the last time you did it for the most part was in geometry. We use formulas. Most of which are actually based on the area of a rectangle being length times width. And you're probably aware of that in terms of rectangles to triangles. probably seen a relationship that shows where the rectangle formula becomes a triangle formula if you cut the triangle in half, that kind of stuff. But it's actually true for circles too. It's a little bit different of an argument, but it's true. So most of that's based on the formula for area equals length times width for a rectangle. So what about calculus? Well, in calculus, we can use the area of rectangles. Still based on rectangles, right? The area of rectangles. To approximate the area under a curve then we let the width of the rectangle approach 0. And I realize this example, along with the one that I did on the board last time, I'm doing a bit of hand waving. I'm kind of saying we can kind of do it like this. And the reason is because we're really going to do it later. But it's just sort of to give you a taste of what we're going to be able to do with calculus compared to what we were able to do with pre-calc. So if you take just a random curve, and I'm going to put it on axes so that we can have some reference point to it. This is kind of my go-to random curve if you haven't already figured that out. And we want to start here. That's really thick. Let me try that a little thinner. We want to start here and we want to go over here. And we want to find the area under the curve. So you can imagine drawing these sort of vertical lines up to the curve itself. And we would like to shade in everything underneath it. But the idea behind that is we could, and not because this is the only way to do it, it's just kind of nice. We could half this, right? We could cut this in half, and we could cut it in half again, and we could cut it in half again. And can you imagine, or can you picture, rather, that this starts to look like little bitty rectangles, right? And the tinier and tinier the width of the rectangles are, the less change there is along the top that's curve. It starts to look straighter and flatter. It's just like when you're on your calculator and you're zoomed in too far and you're like, man, that's a line, and you zoom out and you're like, oh no, it's not, it's a parabola. How did that happen? Well, because you were zoomed in too far, right? So if you zoom in far enough and you minimize the width of the rectangle enough, it starts to look more and more like a rectangle itself. And that means that the area of the rectangle formula becomes closer and closer to the actual area that you're trying to find. And this is the area problem, is taking this and letting there be either rectangles of 0 width or nearly 0 width, or you can say letting there be infinitely many rectangles in that space. Okay, this is the very last chapter we're going to do. We're going to talk about this in chapter 4, but it is where we're headed eventually. So it's another way that we can use calculus instead of having to be sort of stuck in what pre-calculus can provide for us. So many of your questions are going to look just like this one right here, this first question. They're going to ask you to decide if you can do this with pre-calculus or if you have to use calculus. And remember, it's all based on variability. If things are rigid and inflexible, you can usually find them with pre-calculus. And if they're variable and they've got some wiggle room, it's usually a calculus idea. And then what they want you to do is that if it's pre-calculus, they want you to state that it's pre-calculus and find it. But then if it's calculus, they want you to use a graphical or a numerical approach to estimate the solution. And then there's some wiggle room because we haven't really learned how to find those values exactly. And I realize some of you have learned how to find some of those values exactly, but that's not what we're expecting you to do right now, okay? So here's an example. This one says to consider the equation f of x equals 4x plus 3. What is the slope of this curve at x equal to 2? So the first question to ask yourself is that what is this equation an equation of? Whoops. What is this? It's a line. And is a line rigid or is it flexible? It's very rigid, right? You guys have been working with lines since junior high math somewhere along the way, right? An Algebra 1 or maybe even a pre-algebra course. You've talked about slopes, you've talked about distances, you've talked about lots of things to do specifically with lines. It's a very rigid idea, and it's a pre-calculus topic. Does that make sense? If this equation had not been a line, if it had been anything else, maybe it had been sine, or maybe it had been a parabola, or maybe it had been a rational expression, or a square root of a x, right? Something like that, where the equation is a curve instead of a line, this would be a calculus topic, okay? So it's not because it's asking you about slope, it's asking you about a line that makes this a pre-calculus idea. So your answer to start with is that this is pre-calc. The beautiful thing is that the question that it asks, because it's related to pre-calc, is a very easy answer on this one. What is the slope of the curve at x equal to 2? 4. Did it matter that they told you that x is equal to 2? Not in the least, because it was a line. If this had been any other shape, it would matter. Because when you have a curve, the slope would be different. It's like driving in the hills. Have you ever driven in the hills? Yeah, I mean, it depends, right? It depends on how steep the area is where you are right now as to how hard your car is working and the gas mileage and things like that, because it changes. So this one has a slope of 4. And you don't have to calculate anything. You simply know that because you know that this is an equation of a line. So let me show you a comparison for what happens when you don't have a line. Same question, decide if it's pre-calc or calc. And why is it that this one's going to be calculus? Because it's a parabola, i.e. it's not a line, right? It's not a line. So how do we do this? Okay, so this is calculus. Because it's not rigid. It's variable. Parabolas are different steepnesses depending on where you are. If you're at the peak of a parabola, it's flat. I mean, for an instantaneous moment, right? And then you're like going downhill or uphill after that. But for a moment, it's flat, and then it becomes steeper and steeper as you move further away from that peak or that valley. So this one actually matters that it says x equal to 2, right? It matters. If it didn't say x is equal to 2 and it said as x is equal to 4, we would get a different answer than we're going to get. So I'd like to show you how you would go about estimating this, since we are dealing with a calculus idea and we don't have a line so that we can just look at it and say 4 like we did on the last one. So here's how we do this. What we need to do is we need to pick values that are really, really close to the number 2 and see what happens as we get closer. And there's a really nice way to do that that just gives us sort of a fallback on, like, I don't have to make the decisions. It just works this way, and it's very nicely done all the time. Certainly not the only way to do it, but it is a nice way to do it, is to choose values that are very close to 2 on either side. For example, I'll start on the right-hand side with 2.1. Slightly bigger than 2, but it's close, right? Right? It's like a dime difference. Agreed? $2.10. Yeah. And if I want to get closer to 2 than 2.1, a really nice way to do it is to simply put a 0 in between the 2. Now I've got like 2 and a penny, right? A penny is closer to $2 than a dime is closer to $2, right? So what do you think I might do as my third value? Yeah, exactly. I'm just going to put 2 zeros in between there. So the idea about this side is that I'm slightly bigger than 2, but I'm really close to 2. Are you with me? But I can't just do it from one side. I have to do it from both sides to make it actually provable, right? That it really works. That it's not just some sort of fluke that happens if you're slightly bigger than 2. So we do it from the other side as well. So slightly smaller than 2 would be something like 1.9. It's $1.90, right? That's the idea. Like, that's really close to 2, but if you give the clerk $1.90 and the price was $2, it's not going to work. So you try to get a little bit closer and you say, okay, how about like 1.99? So that's like $1.99. That's closer than $1.90. So again, intuition should tell you, what should the third value be? What do you think? Yeah, 3 nines, right? So those are the sort of go-to numbers. If you're dealing with 4, you would do 4.1, 4.01, 4.001, and then 3.9, 3.99, and 3.999. Make sense? Okay. I hope you have a calculator with you today. If not, just bear with everybody else as they help you out. But if you do have a calculator, grab it. What we're going to do with this next column, the one that's in the middle there, it says f of x, is we're going to take that 2.1, 2.01, and 2.001, and we're going to actually plug it into the equation. So the equation at the top, the one that says 3x squared plus 2x minus 4. So we're going to evaluate this equation at 2.1 and so forth down the line. Okay, so somebody tell me what you get when you plug in 2.1 into this equation. Promise it's not a trick question. Oh, let me actually show you one cool thing too while we're at it. Who has TI 83 or 84 kind of version calculator with you? You can do this much quicker if you will put this equation into the graph, like where you would normally graph it. Okay. So if you put it into the y equals area and you put the equation in, we'll do a little calculator fun stuff today. What's my equation? 3x squared plus 2x minus 4. Okay? So you put this in your calculator. And one more bit of fun stuff. And if you don't have your calculator with you today, bring it next time so that we can get yours set up this way. Above the window button, where it says window, it says table set. TBL-SET. Do you see that? Okay. If you will use your second button, you get into that menu, and it will say table setup. The default on these calculators for the table setup is for them to both be selected on it where it says auto. Auto. And when you do that and you look in a table, it actually gives you typically, like as the reset kind of value, 1, 2, 3, 4, 5, and so forth for your inputs for your X values. But it would be much nicer if we could actually tell it that we want 2.1 and 2.01 and so forth, right? The way you get that to happen is where it says auto on the first line under independent, change that one to say ask. So the first one says ask, the second one says auto. And what that allows you to do is it's going to allow us to very quickly put them into the table and just spit out answers instead of having to key them in multiple times. Okay? So if you have that kind of calculator with you today and you can change your table to do that, then you can actually go into the table. It's underneath the graph menu on the top. It says, right above it, it says table. So you can hit second and then the table button, and then you have the ability to have these blank screens on the X's and the Y's. Or if they're not blank, you can delete what's in there, and you can put the numbers in that you want. If you have a scientific calculator like Katie does, and over here, yeah, that's totally fine. There's nothing wrong with it. You're just going to have to do more keystrokes. So that's all. Okay, so whichever kinds of calculator you have, somebody tell me what you get when you put in 2.1. What'd y'all get? That's exactly right, 13.43. Okay, if you don't have a calculator with you today, just jot that down for now. What happens when you put in 2.01? Okay, and we'll write down, I think, right, Anthony, you have a calculator with you, right? If you go on top of that 12.14, actually move your cursor over on top of it, it'll show you at the bottom of the screen more decimal places. So it's actually 1403. So we're going to write down 6 decimal places is usually sufficient to make sure you don't get any errors later on. So we'll go with that. If there's more decimals in the calculator, write more down. That's fantastic. And then the next one, 2.001. What happens? 014, and then actually after that it goes 003. Yeah. So we're getting close to 12, right? I mean, it's getting really close to 12. And then, again, we're going to skip the slope column for now. We'll come back to that in a minute. Let's go over to the f of x with the 1.9 and so forth. What happens when you put in 1.9? 7.63. Wonderful. And 1.99? Perfect. And then the last one, 1.999?
11.98600.
Fabulous. Okay. If you have trouble with calculator, if you're not sure how to change this table or whatever, come see me in my office, go to the Success Center. They're fantastic at using calculators up there because they've been using them for all their math classes too, okay? All right, the slope column. You all know how to find slope. I mentioned it last time. So what is an equation that you remember for slope? Oops. Wonderful. So I will write down one of these. After that, they all work the same way. Oh, we need one more thing. We need the actual value at 2 itself. We didn't do that, and I meant to do that earlier on. So what happens when we actually plug 2 in? What's the function value at our actual point of concern? 12? Yeah. So that's making sense why these f of x values, as you go down these lists, look like they're getting closer to 12, right? It makes sense. I mean, if you're getting closer and closer to a specific value, it should be getting closer and closer on the y-axis to the same value too. Okay, so as we're doing this, we'll do the first one. Our slope value for the 2.11, I'll just call it the number 1 because it's the first one on my list, would be the y2 value. So the y2 value on that one is 13.43. Minus the y1 value, which is going to stay the same every single time, that 12 that we just calculated, over 2.1 minus 2. So as we work our way along, these two are never going to change. 12 and 2 are going to stay the same. All right, so if we calculate that, you need to be careful with using parentheses in your calculator to make sure that you don't accidentally tell it to divide 12 by 2.1. You know what I'm talking about? Like it needs to know that it does the subtraction on top first, the subtraction on bottom first, and then it divides. So if you tell it to do that in the right way, what slope value do you get? All right, so this should be 1.43 divided by 0.1. If you did that by hand, you don't have to do it by hand. But what do you get for the slope value? 14.3. Okay, and we're going to repeat, right? Like the shampoo containers, wash, rinse, repeat. We're going to do the same thing for the second one. But what changes is that the first value at the beginning of the numerator and the beginning of the denominator will change. Now I have 12.1403. On top minus 12, and I have 2.01 on bottom minus 2. So again, if you want to write it out longhand, what I actually have now is 0.1403 divided by 0.01. Okay, you don't have to write all this work out. I'm cool with that not being the case, but this is what's going in your calculator in some fashion, depending on the calculator you have. What do you get for that second slope? Yes, you do, 14.03. Rod Anthony's ahead of the game. 14.003. Depending on the equation, it doesn't always just add a 0 in the middle like that. This one's really friendly because it's a quadratic, but it doesn't always work that way. Okay, same thing. We're going to do the 1.9. So let me write the first one down. So technically, we've done 3 of these now, so this would be like number 4. So on the fourth one here, we have 10.63 minus the 12 over 1.9 minus the 2. If it bothers you to have the smaller numbers in front of the bigger numbers, just switch the numerator around, switch the denominator around. It doesn't matter. You get positive numbers instead of negatives either way. It's going to be the same. So after you do the subtraction and then you do the division, what do you get for your slope when it's 1.9? Mm-hmm. How about the next one when it's 1.99? That's correct. We have one more, 1.999. What's this one going to be? Okay. Those values are correct. If you don't have a calculator with you today, you can confirm those later as you get that going. So so this is like we've done all the hard work, okay? Everything on the screen, that's all the hard work. You don't have to necessarily write any of the stuff that I've written below my table. All of that is just the work that would be done inside your calculator, and I'm fully confident you can do that with whatever calculator you have. And if you're not sure or you're not getting the right answers, come see me, okay? Web assignment's really good about telling you how many decimal points to do something, but if you run into a problem with that or if it doesn't seem to be liking that, let me know. We'll figure it out. We haven't actually answered the question. The question is, what's the slope, right? And we've already answered the fact that we're not going to be able to find it exactly. This is an approximation. It's going to be a really good approximation. It's actually going to find it as the right answer, but we don't really have the ability yet to say we know for sure it's right. We're just guessing that it is. So what we're going to do to guess is we're going to look down these two tables that we've created. As we go down the slope column. And we're asking ourselves as we move down the columns, both of them, what value do we get awfully close to in both lists? 14. So our best guess, our expectation is that the slope is 14. The reality is that it really is 14. We just can't really say it for sure yet because we haven't verified that yet. So we're approximating that the answer is 14. Any questions on that? All right. So that is the end of this lesson, 1.1. If you haven't already been inside of WebAssign, you definitely need to do that tonight, if at all possible. Jared?
Do you have like the class key?
It's in your syllabus.
Okay.
Yeah, it says it underneath the WebAssign part in your syllabus. Yes. Yeah, make sure and get in there. If you have any questions or if you're having difficulty logging in, I mean, really, if you can get in there sometime before I actually leave campus today or, just before I would go to bed tonight would be good so that if there's some kind of a problem showing up that I'm not aware of, that you can let me know and I can get it fixed really quickly. Has anybody been inside WebAssign at this point? Is it working okay? Mm-hmm. Oh, good. That's good to know. So it should work okay for everybody. If for some reason you don't have like the paid for code yet, you can apply for a temporary code, and that's fine too. So you can definitely get logged in whether you have the money to get logged in today or not, okay? This assignment is due on Thursday. I'm still used to a Tuesday, Thursday class with this. On Wednesday, when you come to class. 9 a.m. Wednesday, it'll all shut down and you won't be able to keep working on it anymore. I believe you have 10 attempts at every single problem. If you get past about 5 and it's still not working out, that's time to start asking for somebody to figure out what's going on with what you're doing. Maybe it's an input error, or maybe you've got some actual, arithmetic error or something going on, but you can find out that way. Any questions about what's due on Wednesday? Okay.